Welcome to the GaN Talk podcast, brought to you by EPC and hosted by Maurizio Di Paolo Emilio, Marcom Director at EPC. This show brings to life the stories behind GaN technologies and products. In each episode, you'll hear engineers, executives, and academics share insights on the challenges and opportunities shaping the GaN market. Here is your host, Maurizio Di Paolo Emilio.
Hello everyone and welcome to GaN Talk podcast brought to you by EPC. I am Maurizio, Marcom Director at EPC, and today we are talking about an exciting milestone. So the launch into mass production of the EPC 2366, EPC's first 7th generation GaN power transistors. So delivering up to 3 times better performance than silicon MOSFETs, this breakthrough device is designed for high efficiency, high density power systems. Here to share more about this innovation is Alex Lidow, CEO and co-founder of EPC. Hi Alex, how are you? How's it going?
Hi Maurizio.
Good. So Alex, we published a few days ago the news about the mass production of Gen-7 EPC 2366, so the first of these Gen-7. Can you start by giving us an overview of what makes this 7th generation GaN transistor unique compared to previous generations?
So, we started sampling the 7th generation just to strategic customers about 6 months ago, and now it's going into mass production. The reason it's so important is that it actually breaks through the low voltage barrier that has been the MOSFET barrier. It allows us to actually have 3 times the power density of the best 40 volt power MOSFETs. And it uses very new technology from EPC, and it's fully qualified. So all that technology now has been road tested, and it's wonderful. We see massive design in, particularly in server applications, and that's pretty exciting. I've never seen anything go so fast. But 7th generation is even beyond that. It opens up all the lower voltages to GaN, and it really spells the end of the MOSFET. If you can do 3x better at 40 volts and about the same amount better at 15 volts than MOSFETs, why have a MOSFET anymore?
Indeed, yes. So this device, as you say, delivers up to 3 times better performance than silicon MOSFET. So can you explain what metrics, characteristics contribute to this improvement?
So I'd say the most obvious one is on resistance times area is 3 times better. But we deliver in a 2.6 by 3.3 millimeter package, something that has only 25% the on resistance of the best MOSFET in a 3 by 3. So in a smaller package, we deliver something much better. Okay, so that's great. Now, with the smaller size goes much less capacitance. So the switching capacitance, QGD, is an order of magnitude less. The output capacitance, an order of magnitude less. So now we're really talking about something that can switch faster and has lower conduction losses in a much smaller footprint. And when you're looking at very high density applications like you have on servers, those are critical parameters.
So indeed, so let me also mention the figure of merit in this case that is as a good number as you can find in the data sheet of EPC 2366. So they're talking about applications. So you mentioned extremely low RDS on and optimized RDS on times QG, so figure of merit. So which applications market will benefit the most from these new devices? Any specific sectors where you see immediate adoption?
So there are a lot of applications that use a 12 volt distribution bus. And that means somewhere they convert from usually 48 volts or AC down to 12 volts. Now at 12 volts, if you use a center tap sync rec, you need 40 volts. And center tap is a cheaper solution because it uses half as many transistors. So now a center tap sync rec using 40 volts with GaN is 1/3 the conduction losses and a whole lot less of the switching losses, depending on the frequency that's used, compared to the MOSFET. So that should be a very quick design in, and customers are saying that too. There's also a lot of 12-volt down applications, 12 volts to 3.3, 2.5. Those tend to be buck converters, and they tend also to want 40-volt devices. So we're seeing a lot of those new applications adopting GaN very quickly from our strategic customers. Now everybody can get a hold of them.
So the device comes in a compact packaging. So you mentioned 3.3 times 2.6 millimeter, and so with excellent thermal performance. So can you tell more about this performance in terms of thermal? So can you share why this is so important also for high power designs?
So thermal resistance, if you have bad thermal resistance, your device heats up and it gives you bad on resistance. So for one thing, our GaN devices have exposed back surface that's actually the semiconductor itself. So you can attach very, very efficiently a heat sink to it or any heat spreader to it. The thermal resistance to the heat sink is 0.6 degrees C per watt. Now you can get big devices like 5x6 dual-sided MOSFETs that have about the same thermal resistance to the heatsink. So by going directly to the semiconductor instead of through a bunch of layers like on those 5x6s, you get much more efficient thermal transfer. Plus, we have more, I'll say, copper on the board. In other words, a higher density of connections to the PC board. So if you are able to, you can suck more of the energy out the PC board.
So we are also offering the board, the evaluation board, based on EPC 2366, so EPC 9167. So tell us more about this board. How does this help engineers accelerate the design, testing into real-world application that you already mentioned?
So EPC, whenever they introduce a new product, we introduce an eval board. And the eval boards are a basic half bridge, and they include drivers and some capacitors, so that you can very quickly configure it as a brushless DC motor drive. You can configure it as a buck converter. You can configure it as a sync rec. Any of those things very quickly. And you will get a reasonable evaluation of performance from that. By being, a general purpose device, it's not optimized for any of those, but we have field applications engineer and internal applications that will help any of our customers get to the state of the art.
Yes, good. And so this is the first Gen-7 devices in mass production. In the press releases, you mentioned also 25 volt and 15 volt devices are being sampled. So what can we expect next from the Gen-7 eGaN roadmap?
So first of all, there are 25 volt and 15 volt devices coming that are already sampling to strategic customers. They'll be in mass production in the April timeframe. And we are also coming out with devices in larger packages, 3.3 by 3.3 millimeters. And so the 25 volt will appear in a 3.3 by 3.3, and it will also be in a new package format that has just 3 terminals, drain, source, and gate. And we've engineered a 3-terminal package that has extraordinarily low internal inductance and extraordinarily low internal resistance, so we can deliver you the same high performance as the interleaved configurations we've been delivering up till now.
Yeah, so looking at the wider picture, let's say that the next Gen-7 eGaN devices are transforming the power electronics field landscape and will transform even more, replacing silicon MOSFETs, right?
Yes, I think that silicon MOSFETs, they have big legacy, and the legacy will continue until those designs become obsolete, and that can be tens of years. But when you look at new designs, especially performance, which is like in computing or in robotics or in autonomous machines or in certainly in space, every new design, if the engineer isn't first considering GaN for their new design, they're making a mistake. So as those applications start becoming a bigger share, that's where the growth will be. MOSFETs will grow slower. Eventually, they'll go into decline. And that happened when the MOSFETs replaced the bipolar transistors back in the 1980s.
The EPC 2366 is now in volume production, ready to order through EPC's global channels and direct sales. So both EPC 2366 and EPC 19167 demo boards are available for immediate delivery from DigiKey. So you can check the link in the podcast notes that you can see here in the text. A huge thanks to Alex Lidow for joining us today. Thank you, Alex.
And thank you. That was fun.
Thanks to all of you for listening to GaN Talk podcast brought to you by EPC. See you next time.